Sonja Stimac from Zagreb. And the title of the talk is Densely Branching Trees as Models for Henonlike and Lossy-like attractors. Please.
So thanks to the organizers for organizing this meeting in these hard times, and of course for the invitation. I'm really, really very happy to be here. So, as you already heard, I will talk about densely branching trees as models for Henonlike and Lossy-like maps, and this is joint work with Jan Boroński. First, let me say just briefly what we have proved. So roughly speaking, we have proved that Hénon and Lossy maps on the strange attractors are conjugate to shift homeomorphism on inverse limits of maps of metric trees, also known as dendrites, with dense set of branch points. And for the Hénon maps, this applies to Benedict-Carlson parameter set, which has a positive Lebesgue measure. And for the Lossy maps, the results applies for an open set of parameters given by Misurevich in his paper in 1980. So in general, under mild dissipation introduced by Croisière and Pujals in 2017, in fact, conjugacy holds if the attractor does not have an arc in common with the stable manifold, and the density of branch points holds when the attractor is a homoclinic class. So, in fact, our results can be seen as a generalization of a classical result of Williams from 1967 to the non-uniformly hyperbolic world. And to the best of our knowledge, these are the first examples of canonical two-parameter families of attractors in the plane for which such a one-dimensional locally connected models are given, tying together topology and dynamics. But of course, I want to present you our results more precisely, and to be able to do this, let me start from the beginning with definition, notation, and mathematical timeline. So as all of us know very well, parametric families of maps have been studied many decades so far, but unfortunately, understanding of their dynamics is still far from being well understood. And the most fundamental example in dimension 2 is the Hénon family. HAB notation is in this talk. And the Hénon family takes, let me see, could I use mouse? No. Okay, takes the point X, Y in the plane and maps it, sorry. Okay. Could I have pointer somehow? Or could I show? Maybe in this way. Okay. So Hénon map takes XY point in the plane and map it to the point 1 plus y minus x squared bx. And this is for parameters A and B from the plane, except B cannot be 0 because then it is one-dimensional map. And this family is introduced by Hénon in 1976 in this paper here, mentioned here. So as you see, this formula seems very, very simple. There is only one term which is not linear, and this is ax squared, it's quadratic term. But unfortunately, this map gave the mathematical community, the dynamical system community, a lot of trouble, and in fact, a lot of joy also. So it took 15 years to be shown that, in fact,
Sorry, we can't hear anymore. For the last minute or so. Maybe the microphone ran out of battery or something.
Indeed, we do not hear anything.
yes, I can say something.
Now it's back.
Is it okay now?
Yes.
Yes.
So here you can see Hénon attractor for A equals 1.4 and B equals 0.3. And these attractors are non-uniformly hyperbolic and contain a dense orbit. And in 1993, this approach, Benedict-Carlson approach, was generalized in this paper here to a wider class of so-called Henonlike maps by Mora and Viana. And because these maps are very complicated and hard to study, Lossy came to the idea to simplify Hénon family, and he introduced the family of piecewise affine maps.
Some problem with the sound.
Yeah, again, we cannot hear. Should I say something? Do you hear me?
Yeah, it's possible to hear now.
But it doesn't. Okay. Okay, Lossy maps. So what Lossy did, he replaced quadratic terms with this absolute value of x. This is the only change. And this was really a simplification. But so we have now piecewise affine maps, which is simpler, but we lose differentiability in all points. So now this map is not differentiable at every point, unfortunately. But that it was simple, it shows that it took just 2 years. In 1980, Misurevich proved the existence of strange attractors of the Lossy maps for a large set of parameters. And here you can see Lossy attractor for parameter values 1.7 and 0.5. A equals 1.7 and B equals 0.5. And here you can see the parameter set M. So in 2018, Michal Misurevich and myself, we we slightly extended the original Mihaljevic sets, and it's now like this. And in the same paper, in fact, what was the main goal of this paper is that we introduce the wider class of so-called Lossy-like maps and prove the existence of strange attractors and all analogous results from the Michal papers in 1980. Okay, so this is the first ingredient, Lossy maps and Hénon maps. The second ingredients for our result, to explain our results, are inverse limits. So let me recall now inverse limits. Given a continuous map F on a compact metric space X, the inverse limit of X with bonding map F is given in the following way. So this set is the space of all sequences x0, x1, x2, and so on from the product space x to the n0. N0 is the set of all positive integers, 0, 1, 2, 3, 4, and so on, such that f of xi plus 1 is equals to xi for every I in n0, which means that this point where x is mapped here and x2 is by f maps to x1 and so on. And so this space is a metric space, is equipped with metric induced from the product metric in the product space x to the n0. So inverse limit also comes with a homeomorphism that extends the map F, called the natural extension of F, or the shift homeomorphism, denoted sigma F. And this sigma F is defined as follows. So you take any point x from the inverse limit, and shift of this point is you just apply F to every coordinate. So f of x0, f of x1, f of x2, and so on. But as we know, f of x1 is x0, f of x2 is x1, and so on. Therefore, the name shifts because you just shift all these coordinates to the right, and here you have just f of x0. And it is well known that the natural extension of a map F is the smallest in the sense of inclusion invertible map which is semi-conjugate to F, which means that any other invertible map semi-conjugate to F is also semi-conjugate to sigma F. And so why inverse limits are important in dynamics? This goes to 1967 when Williams showed that manifold diffeomorphism on hyperbolic attractors can be conjugate to the shift on an inverse limit of branch-one manifold. So therefore, inverse limits really very well model these maps. And this is proved in this paper here. And so, inspired and going for a similar result for Hénon maps, Marcy Budge in 1995 proved that for parameter values A, where the quadratic map QA has a attracting periodic orbit and small values of B, the Hénon maps HAB, when restricted to the attracting sets, are topologically conjugate to shift homeomorphism on inverse limit on an interval with bonding map QA. But as we know, these parameters are somehow very special. This parameter has Lebesgue measure 0. So the question is, what for all other parameters? And in 1987, so even earlier, Marcy Budge proved that there are parameter values for which Williams result no longer holds. So for example, for values of A for which the critical point of the quadratic map eventually lands on a repelling periodic orbit, there are arbitrary small values of B for which AHB, the Hénon map, has a hyperbolic periodic orbit with homoclinic tangencies. And for such A and B, the dynamics of Hénon attractor is not conjugate to a natural extension or to a shift map of any map of a branch-one manifold. So the question is, this is showed in this paper. So the question is, which space the simplest space can be used to model the Hénon and the Lossy maps. So because we want to restrict to lower dimension, it's simpler to study models in lower dimensions. So in 2018, Crozier and Pujol showed therefore any A between 1 and 2 and B between -1/4 and 1/4 except for 0, of course, the Hénon map is mildly dissipative on this surface D. This is proved in this paper, and so see, please note here you see strongly dissipative. So in this paper, instead of mildly dissipative, the authors use the term strongly dissipative, but later on they change the terminology because it's more suitable. Because if B is between 0 and 1/4, absolute value of B, you see that this is really a very mild assumption. So mildly dissipative is just better term. So therefore, so I will not go to the definition of mildly dissipative because there are 3 ingredients, it's time consuming and it's not important for this talk. For us, what is important, that this means that for the consequence on the Lossy map is that AHB has a one-dimensional structure in the following sense. Using one-dimensional pieces of stable manifold of almost every point in the surface of dissipation for any ergodic measure mu not supported on a hyperbolic sink, a reduced one-dimensional dynamics is obtained and as a continuous non-invertible map H acting on a real tree T prime. So this is the semi-conjugate model. So this means that there exists a semi-conjugacy pi from a Hénon map restricted to this surface D to this 3 T prime to the map H, which is continuous but not invertible on this real 3 T prime. And moreover, this map pi also induces a map pi star on a non-atomic ergodic measure mu on any non-atomic measure mu, such that the entropy of mu and pi star of mu are the same. So here the real trees is understood as a uniquely path connected metric space. And if you go into this paper, you can see that in fact the 3T prime is also locally connected, which makes them metric trees, also known as dendrites. So it's clear that not all uniquely path-connected metric spaces are not locally connected, and there are even examples which separate the plane, like Warshaw's circle, but metric trees are a plane not separating. And so Jan Boroński and I were able to extend this Crozier-Pujar's approach. And what we have done, so first we focused on Lossy maps. And moreover, we focused on a single stable manifold. Crozier and Pujol consider stable manifolds of almost all points, but we focused on stable manifold of 1 point of fixed point contained in the strange attractor of the Lossy map. And this is, and we focused on Misurevich parameter sets. So let me show you how this looks like. So this in blue, this is unstable manifold. So fixed point is somewhere here. And this blue is unstable, part of unstable manifold of this fixed point. In fact, this is part of attractor of the Lossy map. And this in red, this is part of stable manifold of this fixed point X. And this picture is for This is a computer simulation for parameters A and B as here, 1.75, 0.45. So we have proved that the lossy map restricted to its strange attractor is in fact conjugate to the natural extension of a map on a metric tree. So with this approach, with this restriction, we prove that if you take AB in Misurevich set of parameters and you take lossy map, then there exists a metric tree T and the continuous map F such that lossy map restricted to its attractor is conjugate to the Schiss homeomorphism sigma F on inverse limit of TF. This means that the metric tree T with its map F gives a very good model for dynamics of the lossy map restricted on its attractor. And this is one of the reasons why one would like to understand better the geometry of this tree T. And in that context, we have proved that the set of branch points of T is a dense subset of T. So branch points are dense in T. So from topological point of view, these results, these two theorems imply that the lossy attractor lambda is well-defined in well-defined sense, very well approximated by the densely branching metric tree T in the following way. For every epsilon greater than 0, there exists a continuous surjection G epsilon from lambda to T, such that diameter of G epsilon of diameter of inverse of G epsilon at T is less than epsilon for every T in T. Indeed, since lambda is homeomorphic to this inverse limit, topologically the same, in order to obtain the map G epsilon, it is enough just to take a projection from inverse limit to the ith coordinate space when I is large enough. And the density of branch points means that the topologically T has a similar structure to several well-known fractals. One of them is, for example, this continuous self-similar tree. And our approach is not restricted to C0 world, but extends also to Hénon family when parameters belong to Bendix-Carlson set of parameters. So we have proved the same result, the similar result for the Hénon map. So if parameters are from the Bendix-Carlson set of parameters, then there exists a metric tree T prime and continuous map H such that the Hénon map restricted to its attractor is conjugate to the natural extension sigma H on inverse limit of T prime H. And the set of branch points of T prime is also dense subset of T prime. And again, this leads to the conclusion that densely branching trees T prime well approximates the Hénon attractor lambda prime in the same sense as I already said for the lossy maps. And as I already mentioned in the few first minutes, our approach is by no means limited to the Hénon and Lossy family of maps. All statements generalize to Henonlike and Lossy-like maps as well. And for the mildly dissipative maps, the density of branch points holds when the attractor is a homoclinic class, and conjugacy holds if additionally the intersection of the attractor and stable manifold does not contain a non-degenerate arc. And so from everything said, a few, in my opinion, very interesting questions arise. Recall a branch point B in 3T has order n, and n is of course greater than or equal to 3, if T minus B consists of n components, connected components. And so the first question is, are there parameters A, B in Misurevich set of parameters such that all branch points of the metric 3T for the lossy maps have order 3. We do not know that. So if yes, so this is the case for this example. So if yes, is there a metric D on T related somehow to the dynamics of the lossy map such that TD is the continuum cell similar tree? Also, the question is, are there parameters A, B in Misurevich set of parameters such that the metric 3T of the lossy map LAB has at least one branch point of order greater than 3? And in this case, is there an upper bound on the order of branch points? We do not know that also. And of course, the same questions can be asked for the Hénon maps for parameters in BC. And I'll finish a little bit later, but would be good because lunch is after my talk. At the end, let me mention one additional feature of strange attractors that we have proved. So for AB in Misurevich set of parameters, the strange attractor of the lossy map is indecomposable. And the same holds for the Hénon maps when HB is in Benedict-Carlson set of parameters. So that's all. Thank you.
Of time. Do you hear me? We have a lot of time for discussion, so I'm waiting for questions, remarks, comments. Remote? Don't sleep. There is a question where
Ready?
Sorry, can you hear me?
Sorry, we have a question from our.
Yes, just for understanding, I mean, Causifier and Pouchard's proved that the factor, the map is non-invertible, right?
Pardon? Yes, the map is non-invertible.
Exactly. In your case, you get it's invertible, right? You're proving it's the shift, right? That you conjugate to.
Sorry, I don't hear you.
Okay, maybe it's better.
Yes.
Okay, and you prove that it's you on the factor you actually have the shift, so it's invertible, right? In your result.
Sorry, I hear you but don't understand the words.
Okay, okay, maybe.
I understand. Don't hear words.
Is the factor map? It's invertible, right? That you get.
The map is invertible.
No, sorry, your factor map. This is shift, right? The normal shift, right? On the factor map. No, the factor that they get.
You think factor map on the inverse limit on the 3 is not invertible? It's continuous there only.
Yes. Exactly, and I wanted to ask where do you get this better information than compared to Pouchard's and Causifier?
Yes. I'm trying to hear. So I hear some noise, but cannot recognize words because.
Yeah, I'm sorry. Yes. Can you make this factor somehow unique up to conjugacy? I mean, is there a way of thinking that's the biggest factor in a certain sense? Okay. Yes. Okay. And the other question I have is respect to the metrics. Is there in any way to identify a special metric? I mean that has some unique property that is more important than other ones. I mean,
You think on the
yes,
tree?
on a tree. Yes. That.
So we have some ideas, but
Okay.
Yes, so I just wanted to say that, so, I mean, we came up with some metrics, but we're still looking into that to actually make it, capture some features of the dynamics. So, I mean, ideally, you would like that metric to somehow depend on the parameter as well. And this is not obvious how to do it. Yeah.
Okay, thank you.
So sorry, can you hear me?
Hello. Yes, you can.
Yeah.
You can ask.
I wanted to ask, so you have the Lossy attractor then to this inverse limit on this tree. So what is the map on this tree that you have there? I mean, can you say something about it? I mean, I would guess for a tree, you don't have many maps. You would sort of, imagine that you have a branch point and you sort of, wrap the branch point around. Is that the right picture I have in my head, or what is the map on this inverse limit on the tree, the bonding map there?
So the map on the tree is induced by Lossy or Hénon map on the attractor, because when you squeeze all these segments of a stable manifold, then you know which point will go where, and this is a way how you obtain your map on a tree.
Right, but I mean, so when I mean, I know that because that's what your theorem says, right? But I mean, if you just have your tree, I mean, there should be like, I mean, is there like an easy way to understand this map on the tree? So I would sort of, I mean, so like I guess many trees we have in our head are sort of, let's say, I don't know, let's say z squared plus I, the Julia set, and we know very well how the tree maps to itself. And is that, does it map to itself in a similar way, or is it, a more complicated way? So for example, like, is there like, I mean, is there like a finite number of, let's say, critical points where this map would not be locally injective, or is it, an infinite number of such points? Or can you say something about what this map is, or how it behaves?
We don't have a lot of so far we don't have a lot of information about this map. I think we didn't study it very carefully, but it should be something like, for example, for Lossy maps, something like 10th map or interval, but just on tree. Should have somehow one band.
So that means that there would be like a unique critical point, if we want to call it the critical point, right?
Yes.
Okay.
So there is a question also from Michael Benedicts. Can you...
I'm trying to speak, but
we can hear you now.
Yeah. So I was thinking, if you is there any chance that your approach would go beyond the Miserevich parameter losses, or my parameters with Carlson for Hénon? This would, of course, be a very, I mean, there is this Ishy combinatorics for Lossy, for instance, and how does your work relate to that? And there is a pruning front of Cvitanovic, which is, I never completely understood it, but did you try? Do you have any ideas what could be beyond the trees at all? I mean, it's a bit too vague question, but
our result is very recent, and you know, we still we're not able to go much further.
No one that really did, right? In some sense. But it might be, this point of view might be interesting to go further. Say for Hénon, I mean, at least close to our parameters, it's not so much, Collison and my parameters, not so much has been progress. There has not been so much progress, right?
Yeah, as you know, it's a very hard question.
Yeah, no, it's too hard question maybe, but that's what I thought about. It's interesting to compare notes, and Lossy might be better, that you could say, maybe say something about beyond the Mr. average parameters for Lossy, for instance. Do you have some similar model? But maybe it's too vague question and too, I mean, I just thought of it when I heard the talk. Maybe it's a too difficult question.
Okay, are there some further questions from remote participants? Okay, maybe some questions from our lecture room. If no, thanks the speaker again. And now we really approached the time of lunch.